In this lecture, we want to introduce a powerful technique for proving theorems and useful formulas, known as induction. Consider the following two assertions. 1. For any natural number n, the sum of the natural numbers from 1 up to n is given by the ratio n times n plus 1 divided by 2. We can write that out in summation notation as follows. Assertion 2. The sum of the cubes of any 3 consecutive natural numbers is divisible by 9, i.e., start with any natural number n and add up n cubed, then n plus 1 cubed, and then n plus 2 cubed. The sum of those 3 numbers will always have 9 as a factor. In fact, each of these statements represents an infinite number of assertions. Let's work on the first one. For n equal 1, it asserts that 1 is the ratio 1 times 1 plus 1 over 2, which turns out to be 1. Certainly true. For n equals 2, it's a new assertion. It says that 1 plus 2, the sum of the first 2 natural numbers, is the same as the ratio 2 times 2 plus 1 divided by 2, which reduces to 3 equals 3. And if you check it for any n, it turns out it's true. Here is n equals 6. You add up the numbers 1 plus 2 plus 3 plus 4 plus 5 plus 6, and you get exactly the same as 6 times 6 plus 1 divided by 2. That is 21. But the question is, how do you prove that this formula really works for all n? In section 2.4 of the written notes, we give a very clever method. In this lecture, we show a more general method called induction. Before we get into proofs, let's look at the second statement and see how it looks for various n. For n equals 1, it claims that 1 cubed plus 2 cubed plus 3 cubed is divisible by 9. And sure enough, it adds to 36. For n equal 2, that's 2 cubed plus 3 cubed plus 4 cubed, the sum is 99. Again, a multiple of 9. And just one last check, n equals 3. 3 cubed plus 4 cubed plus 5 cubed adds up to 216, and if you check, it's divisible by 9. In both of the cases above, we have a formula that we verified enough to believe it, but we haven't proved it. The answer for infinite sets of assertions like this, when they're indexed by the natural numbers, is to use the method of induction. An excellent visualization of how this method works is to think of a huge line of dominoes standing on n, set up so that if any domino falls in the line, the next domino in the line is hit by it and also falls. It follows that if you knock over the first domino in line, then every domino will eventually be knocked over. So there are 2 key components to the assertion that every domino falls. A, the first domino must be knocked over. B, if any domino is knocked over, it knocks over the next domino. This is exactly the method of induction when we translate this picture into mathematics. In the case of that first assertion, we claimed that the sum of the numbers k from 1 to n always gave you the number n plus 1 over 2. It is true, as we saw above, for n equals 1. That's the first domino falling. But what is the equivalent mathematical idea for the second part? That if one domino falls, it hits its neighbor and causes it to fall. The equivalent mathematical statement is, if the assertion is true for a given value of n, then it is true for the next natural number n plus 1. We have to prove this for any natural number n. You can't show that if it's true for n equals 3, it follows it as true for n equals 4. This is the hard part of proof by induction. Now suppose that this formula is true for a given value of n. So we write down given 1 plus 2 plus 3 up to n is nn plus 1 over 2. And we can take that as a fact, and we're talking about a very specific n. We have to show that if this given formula is true, then it must follow that the formula for n plus 1 is valid. So we need to write that down, and we'll call it to prove. So we must show that it follows from given that 1 plus 2 plus and so on up to n plus 1 gives you the next version of the formula, which is n plus 1 times n plus 1 plus 1 divided by 2. Now we have to start with what we're given, and we have to somehow end up with what we're trying to prove using legitimate mathematical manipulations. The easiest way to do this is to convert the left side of given to the right side of to prove, and that's easy. Just add n plus 1 to both sides of given. So when we do this, the left-hand side of given becomes the left-hand side of to prove. We just get an n plus 1 added. On the right-hand side of given, we had nn plus 1 over 2, and now we're adding to that n plus 1 in order to preserve the inequality. But that right-hand side can be simplified into a single fraction, and when you clean it up and factor it, you get n plus 1 times n plus 2 divided by 2, which is exactly the formula we wanted for the case n plus 1. So we have shown that if the formula holds for any specific n, it will also hold for the next natural number n plus 1. We have also shown that the formula holds for n equal 1. Then it must hold for the next number 2. Then it must hold for the next number 3. And eventually every domino falls. That is, the formula is true for all natural numbers n. Any induction argument requires some artistry in getting to the next domino. Let's have a look at our second problem. The assertion that the sum of the cubes of 3 consecutive natural numbers is always a multiple of 9. We checked the case n equals 1 early. We added up 1 cubed plus 2 cubed plus 3 cubed, and we got 36, which is, of course, 9 times 4. Now suppose that the formula is true for a given natural number n. We write given n cubed plus n plus 1 cubed plus n plus 2 cubed is 9 times some number p, p being a natural number. We now have to prove that from this it follows that the formula will hold for the next natural number n plus 1. That is, we must prove that n plus 1 cubed plus n plus 2 cubed plus n plus 3 cubed is 9 times some natural number r. To manipulate given into something resembling to prove, we can subtract n cubed from both sides of given and add n plus 3 cubed to both sides of given. This manipulates the left side of given into the left side of to prove. What we end up with is a valid formula since we started with given, and it looks like this. N plus 1 cubed plus n plus 2 cubed plus n plus 3 cubed is 9 times some natural number p minus n cubed plus n plus 3 quantity cubed. If you've forgotten how to expand n plus 3 cubed, you can review it, but what you get is n cubed plus 3 times n squared times 3 plus 3 times n times 3 squared plus 3 cubed. So you replace the quantity n plus 3 cubed by that, and then you clean up the whole mess, and you end up with a multiple of 9, namely 9 times p plus n squared plus 3n plus 3. Definitely a multiple of 9. So again, we've shown that for n equals 1, the assertion is true, and that if it's true for a specific n, it follows that it's true for the next natural number. And that is induction in a nutshell. You have an infinite list of assertions. You must verify that the first assertion is true. Then you must verify that if any of the assertions is true, the next in the list will follow. It is simple and beautiful when it works, and sometimes it is more art than science to carry out that second step. Do you have to be careful? You bet. Here is an example of the misuse of induction, in which we will show that all students at a given university are exactly the same age. The example is in essence due to the famous George Polya. So the assertion is that all students at any given university are the same age. Step 1, n equals 1. Okay, you have one student. Obviously, all students in your university are the same age. Step 2, suppose that for some given n, any collection of n students are the same age. Now that means any collection that you select from the student body that contains exactly n students will all have the same age. Now you have to show that the same will be true of any collection of n plus 1 students. So you take a set of n plus 1 students, and let's just number them 1, 2, 3 up to n plus 1. And we're going to choose two subsets from those n plus 1 students. Subset 1 will be the students with numbers 2, 3 up to n plus 1. Notice that that set contains exactly n students. Subset 2 will be the students with numbers 1, 2, 3 up to n. Subset 2 also contains exactly n students. Now we have decided that we're starting with a given statement, any collection of n students are the same age. So all the students in subset 1 are the same age, and all the students in subset 2 are the same age. But those two subsets have non-zero intersection. For example, student number 2 belongs to both. Therefore, all the students in both subsets are the same age, and that includes all the students numbered 1 through n plus 1. Obviously, this is nonsense. To see where the induction fails, look carefully at the case n equals 2 and see that our argument fails in that case. Induction can be used to prove the following list of useful formulas. First, summation k squared from 1 to n is n times n plus 1 times 2n plus 1 over 6. And we have a formula for summation k equal 1 to n cubed. In fact, that's just the square of the formula for summation k. That is, it's n plus 1 over 2 squared. And also, we have a formula for summation of powers of a fixed number r. If you add up the numbers r to the kth power, starting with k equal 1 and ending with k equal n, here r is a given fixed number. That's the same as the ratio r minus r to the power n plus 1 divided by 1 minus r. And this works for any r different from 1. Obviously, when r equals 1, the sum is just n. I want to discuss each of these, and we'll start with the last, which is called the geometric sum formula. First of all, to clarify what it is saying, pick a specific value of r. Say r equal 1/3. Then what this formula claims is that if you form a sum of successively higher powers of 1/3, stopping at, for example, the 200th power, then 1/3 plus 1/3 squared plus 1/3 cubed, and so on, stopping when you get to 1/3 to the 200th power, that's the same as the ratio 1/3 minus 1/3 to the 201st power over 1 minus 1/3. If we had chosen r equals 2 instead of r equal 1/3, then the formula still works. With n equal 200, for example, it would state that the sum 2 plus 2 squared plus 2 cubed, and continue until you get to 2 to the 200th power, is the ratio 2 minus 2 to the 201st power over 1 minus 2. The point is that this formula applies whenever you add up the successive powers of a given number, as long as that number is not 1. Notice that the successive terms being added are each got by multiplying the preceding term by the number r. That is, you started with r equals 2, for example, and the next term being added was 2 times that, namely 2 squared. And the following term to be added is 2 cubed, which is got by multiplying 2 squared by 2, and so on. Each successive term in the sum is just 2 times its predecessor. When the successive numbers of a sum are got by multiplying by a fixed constant, r, the sum is called a geometric sum. The geometric sum formula is often written starting with k equals 0. The sum from k equals 0 to n of r to the k is the ratio 1 minus r to the n plus 1 over 1 minus r. This formula can be derived from our geometric sum formula by adding the extra term r to the 0th. So for example, you start with the sum k equals 0 to n of r to the k, and you write that as r to the 0, the first term, plus the rest of it, summation k equal 1 to n of r to the k. R to the 0 by definition is 1, so you have 1 plus summation k equal 1 to n of r to the k. And that's 1 plus, by our formula, r minus r to the n plus 1 divided by 1 minus r, and you clean that up and you get the formula that we want. It will be a good drill for us to run through the proof of this important formula. You can use induction, but there is a more clever approach. Use the symbol capital SN to represent this sum. Sn is r plus r squared plus r cubed plus r to the n minus 1 plus r to the n, the whole thing written out longhand. Then multiply by r. r times Sn is r squared plus r cubed plus and so on up to r to the n plus 1. In other words, it's almost the original sum Sn, except that you start a little later with r squared and you go a little further all the way to r to the n plus 1. So when you subtract these two expressions, you're going to get a lot of cancellation. In fact, what you get is Sn multiplied by 1 minus r on the left side equals r minus r to the n plus 1 on the right. Everything else canceled out. Solve for Sn and you're done. Now, to the formulas we labeled 1 and 2 earlier. The proofs are straightforward examples of induction, so we will not go through these in the lecture. But the real question is this: how does one guess these formulas in the first place? The answer is we use telescoping sums. A telescoping sum is a sum that is given as a long expression, but when you simplify it, it collapses to the sum of 2 or 3 terms, much like a telescope. An example is the sum from k equal 1 to 20 of the difference between k plus 1 squared and k squared. So that starts off when k is 1 as 2 squared minus 1 squared, plus 3 squared minus 2 squared, plus 4 squared minus 3 squared, and so on. And you stop when you get to k equal 20, where you write down 21 squared minus 20 squared. Now, if you look carefully at this thing, you'll see that virtually everything cancels except the very last 21 squared and the very first minus 1 squared. So this entire sum collapses like a pirate's telescope to the difference between 21 squared and 1 squared. Earlier on, we used induction to prove a formula for the sum of the natural numbers from 1 to n. The sum from k equal 1 to n of k is just the product n times n plus 1 divided by 2. Here is how that formula is discovered and proved in one step using a telescoping sum. We just showed that if you add up the numbers k plus 1 squared minus k squared, starting with k equal 1 and stopping at n, well, n was 20 there, but for a general n it still works, you get the difference n plus 1 squared minus 1. And of course, when you expand n plus 1 squared and clean things up, you get n times n plus 2. Now, inside the sum, expand the quadratic k plus 1 and use the properties of summation to rewrite the left side. The sum from k equal 1 to n of k plus 1 quantity squared minus k squared is the same as the sum from k equal 1 to n of k squared plus 2k plus 1 minus k squared. The k squareds cancel, and you're left with the sum from k equal 1 to n of 2k plus 1. And we know from our general properties of sums that this is twice the sum of the numbers k from 1 to n plus the sum from 1 to n of the number 1, which is just n. So we put all this together And we now know that twice the sum from k equal 1 to n of k plus n is equal to n times n plus 2. If you subtract n from both sides and divide by 2 and clean things up, you get the summation k equal 1 to n of k is the product n times n plus 1 divided by 2. To get the formula for the sum of the squares of the natural numbers from 1 to n, we use the same idea, but starting with the third power rather than the square, and again the sum telescopes. That is, we write down summation k equal 1 to n of the difference k plus 1 cubed minus k cubed, and that telescopes to just be n plus 1 cubed minus 1. The left side can be somewhat painfully expanded. K plus 1 cubed is k cubed plus 3k squared plus 3k plus 1. And we're subtracting k cubed from that. So the left side becomes the summation 3k squared plus 3k plus 1. And that simplifies to become 3 times the sum from k equal 1 to n of k squared plus 3 times the sum from k equal 1 to n of k plus the number n. Equating this expanded left side to the telescoped right side, we have 3 times the sum of the k squareds plus 3 times the sum k plus n is equal to the difference n plus 1 cubed minus 1. Now you have to use the formula for the sum from k equal 1 to n of k, which we have previously derived, and then solve for the sum of the numbers k squared. So you get 3 times summation k squared plus 3, and then instead of summation k, you get n plus 1 over 2, and then plus n, is equal to n plus 1 quantity cubed minus 1. And you can solve for summation k squared. It will be 1/3, and then a big mess, n plus 1 cubed minus 1 minus n, minus 3 times the fraction n times n plus 1 over 2. And when you somewhat painfully clean this up, you have your formula. Now, one of the most important uses of summation notation is to allow us to evaluate or approximate areas. This will be a major topic later on, so for now, let's just look at a very simple introductory example. The problem of determining the area under a graph of the parabola y equals 3x squared plus 1 over the interval 0, 2 in the Cartesian plane. This problem was actually completely solved by the French mathematician Pierre Fermat in 1636, half a century before the discovery of calculus. At this stage, we're going to show how to find the approximations to this area to as high a degree of accuracy as you please. The idea is to break up the interval, the precise phrase is partition the interval, into n equal subdivisions, each of length 2 over n. We then draw a bar graph of a function which is constant on each subinterval. What height should we pick for the bar graph? Well, we can most easily use the left or right endpoint where it hits the graph of the function. Let's use the right endpoint of each subinterval to be definite. The only tricky part here is to see that the coordinates of the right endpoints of the subintervals are given by xk as k times 2 over n, starting with k equal 1 and ending when k is n. Then, to approximate the area under the graph of y equals 3x squared plus 1 over the interval 0, 2, we can add up the areas of the rectangles which form the bar graph. The base of each rectangle has length 2 over n, and the height of each rectangle is just 3 times xk squared plus 1, the y value, to get up to the graph. So the total area under the bar graph is the sum, k equal 1 to n, of 3xk squared plus 1 times 2 over n, where xk is given by k times 2 over n. For n large, this should be a good approximation to the area under the graph of this function, y equals 3x squared plus 1, over the interval 0, 2. But we can use our knowledge of summation formulas to actually evaluate this sum very quickly for any n. We write the sum as an, a standing for area under the bar graph, as the summation k equal 1 to n of 3xk squared plus 1 times 2 over n. That's just the area of the rectangle. And that turns out to be, when you put in k times 2 over n for xk and clean it up, you get the summation from k equal 1 to n of 12k squared over n squared plus 1, all multiplied by 2 over n. Again, you can write that as two distinct sums. The sum involving k squared is 24 over n cubed times summation k squared from 1 to n. And then there's the sum of the numbers 1 from 1 to n multiplied by 2 over n. So you clean all of this up, and you get a simple formula, 4 times n plus 1 times 2n plus 1 over n squared plus 2. Now the power of abstract mathematical notation becomes apparent. We have a simple formula for estimating the area under this curve by the area under a bar graph for any n. I can just as easily use 10,000 rectangles as 10. In fact, here are some values for the sum of the areas of the rectangles for various values of n. For n equal to 10, A10 turns out to be 11.24. For n equal 100, I just plug n equal 100 into our simple formula, and I get 10.1204. And if I plug in n equals 1,000, I get 10.012004. And for n equal 10,000, I get 10.0012004. I hope you can see how this powerful notation, combined with some elegant and useful formulas, allows us to carry out very intimidating calculations in a very easy fashion.